The next presentation was supposed to be made by Dr. Behnam Jafarpour of the University of Southern California. Unfortunately, he's attending to an emergency situation. Really appreciate one of his PhD students who just got caught up last minute, and he's ready to talk. And of course, not necessarily knowing all the slides, he may have to skip a few and hope that you'll tolerate. Please welcome Liu Yingxiang to give his presentation. Thank you.
Thank you. Can you hear me?
Yes, we can. Please share your...
I'll share the slide.
Yes, we can share full screen. Thank you.
So hello, everyone. My name is Yingxiang Liu. And so the plan was to have two people present this work, but since the other PhD student doesn't show up, I'll go over all the presentation. And so I may need to skip some of the slides since I'm not familiar with some of the results. And the topic for this presentation is the dynamic neural network model for prediction and optimization of geothermal energy production. And this is the work. So there are two main research areas. The first one is related to the surface part, which is the power plant. So in this part, we want to do the fault detection of the geothermal power plant. And also we want to build a controller, the MPC controller for automation of the power plant. And the second part is related to the subsurface part, in which we want to build a predictive model to predict the dynamics of the some of the measurements from the subsurface. And we also want to build a closed loop control for the geothermal reservoirs. And so in this project, we have a team from the USC side, and we also have an industrial partner, which is Circ Energy, who provides us some of the real data sets and will also give us some suggestions in our research. And so for the first area, which is related to the subsurface side, and so I'm not too familiar with this part, so I may need to skip some of the slides. And this is the field we are working on, and there are some pictures showing the field, and so we have two models. The first one is we have built a simulation model, and we also have a deep learning model, which both of the model can make predictions. So we can validate some of the prediction results and also the optimization results from the deep learning model using the simulation model here. And for the deep learning model, the structure is showing on the right. So we have a RNN structure, which encodes the past measurements. And we also have for the encoder is CNN, and for the RNN is the decoder, which decodes the future vector from the CNN to a set of predictions. We use this model to make the prediction of the subsurface measurements. And the plots on the top shows the raw data we have given to us by the Circ Energy. And there are some observations. The first one is the frequency of the data is relatively high compared to the frequency of the features. And also there are some variation introduced by the shut-in periods. And as a result, in order to make prediction of the long sequences, we can smooth the data to the weekly data, from the hourly data to a weekly data set in order to make the long-term prediction. And we can also skip some of the parts which the well is shut in, so in order to make a smooth prediction. And this is the prediction results from the neural network model we have. The plot on the top shows the short-term prediction using only the historical data. So the prediction for these two variables, the BHP and the empathy, is pretty accurate to the true measurements. But for the long-term prediction, only relying on the historical data is not enough. We are not able to get a very accurate prediction result. So as a result, we use some of the historical simulated data set from the simulation model we have in order to make the long-term prediction and to train the neural network. And the plot on the bottom shows the long-term prediction results. And since we have the neural network ready, and the next step is to do the optimization on the subsurface site. So there can be many different objective functions. For example, we can maximize the net power generation. We can also minimize the max temperature changes and also the average temperature changes. And this equation on the right corresponds to this objective functions. And for the control variables, we have two control variables for each well, and they are the injection rates and the production rates. We also need to have some constraints to formulate this objective function. And the constraints are the total production rate and the mass balance, and also the upper and lower bounds on how much the pump can produce and inject. And so this is some of the results we have. So we are able to make some improvements in the net power generations. And so maximizing the net power generation, and the result shows that at the same time we can improve the temperature reduction. And so this leads to the sustainable production. And for this slide, so we have encountered some problems of the extrapolation, which means the optimal value is higher than the value in the training data set, which means the neural net model hasn't seen this high value which above this horizontal line here. So some of the prediction results may not be accurate in this range of the data. But in general, the prediction are acceptable during the optimization. We are able to make some improvements in the optimization using the neural network model. And so one of the advantages of using the proxy model for optimization is the speed. So we're able to, so compared to the simulation model, both of the model converges to the same value. So which means using the proxy model doesn't affect the quality of the optimization. But what we have gained is the computation speed. So we can do the optimization faster by using the proxy model from the neural network compared to the optimization in the simulation model. And so that's all for the subsurface side. And so I will talk more about the power plant, which is the surface part. So there are two main objectives. The first one is to predict faults in the geothermal power plant. And we also want to do the model predictive control to control the power plant operations. And so in order to achieve these two objectives, we need a neural network model to do predictions and also to learn the dynamics in the geothermal power plants. And in order to train this neural network model, we have two sources of data. The first part comes from the field, which is given to us by the circuit energy. We also build a HYSYS model, which is a simulation model to generate some data. Also, we can validate some of the prediction results and the control results in this more controlled settings. So with these two sources of data, we can build a neural network model to do these two tasks. And the neural network model, in this case, we designed it and call it like the dynamic neural network model, which consists of three parts. The first part is an encoder which captures the cross-correlation among different measurements to enable the dimensionality reduction and the latent space representation. And so after the original measurements are mapped into the lower dimensional latent space, we use the latent space dynamic model to do the predictions and to describe the evolution of latent states and also the effects of the control variables on the latent space. And so after the predictions are made in the latent space, a decoder structure is used at the end to map the prediction results back to the original data space. So we can do multiple steps ahead prediction in the latent space and map back to the original data space. And for the fault detection, so there are several steps involved in the fault detection procedure. So first, we want to train a neural network model using the normal data set, which means the data set doesn't contain any faulty data. So we can learn the normal variation and the normal trends in the data. And after the predictions are made, we introduce some of the statistical monitoring techniques used in the chemical process domain. And so one of this is called the SPE, which is commonly combined with the principal and component analysis to do the fault detection. And we can calculate this SPE indices based on the prediction result of the neural network model. And we can also calculate a control limit based on the SPE. So this control limit is similar to a threshold or a bounds on the normal variation of the errors. So if any sample is above the control limits, we regard it as the faulty data set. And if the sample is below the control limits, we think it's the normal data. And so this plot shows an example of the use of the SPE. The horizontal line is the control limits. So everything above the horizontal lines are regarded as the faulty data points. And so we want to validate the result of the fault detection procedure we have developed. And one of the data set given to us is the pump data. We have a known fault happens in this pump, so we can validate the results using this part of the data. And so the plot on the top shows the prediction results on the pump data before a maintenance is done to the pump. And the plot on the bottom shows the prediction result after the maintenance. The fault actually happens at the end of this part, so it doesn't happen right after the maintenance. But due to the maintenance, so there are many things are changed. For example, it can be the recalibration of the sensors. They can change some of the old components to new components. But the model doesn't know this information. Therefore, there are some offsets introduced in the prediction. But the model is able to capture the general trend of the data. And we're able to detect the faults before the occurrence using the SPE and the statistical monitoring techniques. I don't think I have a plot of the results here, but we are able to detect the occurrence fault around the end part of the data. And so that's all for the fault detection. And for the MPC, the goal is to using the dynamic neural network model for the model predictive control. And we want to solve an optimization problems to give us a set of future control trajectories based on the future predictions. And the goal is to maximize the net power generation of the whole power plant while maintaining the stability of the operation. And this is the overall workflow of the MPC part. So first we have the binary power plant. We collect the data from this power plant. And also we have on the right, we have a simulation model which can be used to generate the synthetic data sets. And a neural network model is trained using these two sources of data. And we have a set of future prediction states from the trained neural network, and the future prediction states is fed into the MPC. The output of the MPC is the future control trajectory, which maximizes the net power generation, and we can apply the control settings to the power plant, and at the same time we can validate the control result using the simulation model to make sure that the control doesn't destabilize the whole power plant. And for this example, we have 23 measurements from the data set, and we selected 3 variables as the control variables, which is the fan speed, the IGV set point, and also the pump speed of the working fluid, the R134A. And in this system, we have 2 main disturbances. The first one is the in-lab run temperature, which is coming in from here. The second disturbance is the changes in the ambient temperature, which can affect the efficiency of the geothermal power plant. And here we show some fitting results and the prediction result on the data. And the plot on the top shows the control settings and also the disturbances in the system. The disturbances involve the ambient temperature and the brine inlet temperature. And the plot on the bottom shows the prediction result. And this is the 12-step prediction result for some of the variables. The green part is the prediction result for training, and the yellow lines are the prediction results for the validation data set, and the red lines are the prediction results for the testing data set. And from this result, we can see that the neural network model is able to capture the general trend in the data, and we can build an MPC controller based on this proxy model. And this is some of the preliminary results of the MPC. And the plot on the top left is the variable which is connected to the objective function. This variable is the net power output, and the black line here is the output before applying the MPC, and the red line here is the result after applying the MPC controller. So we have an average of improvements in the net power generation, which is about 4%. And for the rest of the plots, the red line is the controller settings given by the MPC, and the black line here is the control setting result before using the MPC. So there are some changes by solving this optimization problems. And so the result shows that the MPC tries to increase the pump speed, so opens up the IGV, and also at the same time decrease the condenser fan speed. So when the ambient temperature is relatively low, so this result makes sense, since when the ambient temperature is low, we don't need to turn up the fans for the condenser to cooling the R134. And since the temperature of the R134 is lower, we can pump more into the system by increasing the pump speed, which can improve the overall power production. And for the conclusions, so we have done applied the deep learning methods on the 2 parts, which is the surface and subsurface part. And for some general observations, so first we learned that the deep learning models are pretty easy to train and to deploy on the field applications. So what we need is some of the real data from the field to train this neural network model. And for the short-term prediction of the neural network model, just by only using the historical data, field data, or generally acceptable. But for the long-term prediction, we may need some additional data sets coming from the simulation model or more data sets collected from the field to make accurate long predictions. And as I mentioned before, the extrapolation, there are some extrapolation issues with using the neural network. So if the range is not seen by the neural network during the training, the prediction result may not be accurate. So as a result, we are planning to introduce some physics and combine the physics with the neural network model to make more accurate predictions when the range is outside the training data set. And I think that's all for my presentation. And so I'm happy to answer any questions.
Wow, thank you very much, Yingxiang. You've done a marvelous job given the short notice and finish your talk in good time. Thanks for stepping up. So if there's any questions, please feel free to post them on the Q&A. I have a question to start with. If everything goes smoothly, there's no fluctuation, and it's really hard to learn anything. So is there a plus or minus percentage of fluctuation that you would need in the data to help train your data set?
So you mean, so if there's no variation, it might be easier to train the model since there's no noise.
Well, everything's constant, right? So unless there's a trigger, something happens, then you get a big, variation in production performance and whatnot, then you'll know something. So I wonder, if the plant is operating smoothly, there's nothing to really train because everything's constant. Correct?
So you mean this is for the fault detection part, right?
Yeah.
Yeah.
Is it detection? Yeah.
Yeah, the goal is to learn the normal dynamics of the power plant. So if there's nothing happens, we learn that. So as a result, if something happens, there are some deviation in the prediction.
Right.
Yeah, we can. Yeah, so whether if there is a variation or not, as long as normal dynamics, we learn it, and as a result, we can, when something bad happens, that there are different shows up in the prediction.
Yes. So I think as companies are ramping up in the geothermal space, energy space, helping with the plant operations, understanding subsurface running simulation is extremely helpful. Okay, so there's I think, let me see, from Isabella Oliveira. Hello, I'd like to know what type of simulator are being used. Is it a black oil or compositional? Thank you.
I'm not too familiar with this, but for the surface part, we use the HYSYS. But for the subsurface, I think we use the tetrad model, which is introduced to us by the Circ Energy, since they use this tetrad model to do the simulation on their part.
Yeah, so I suspect if it's Petrel, it would tie into Schlumberger's Eclipse simulators, or the, what you call that, AlphaSet or something, to take it to the surface, and your HYSYS model will look after that from there. Okay. Any further questions? If not, we thank you again, Xinxiang or Yingxiang. So we'll take a 6-minute break before the next talk.